So, just looking at the program and the current situation, we have. Hold on. Yeah, just we have some of our speakers. We have the slides, but we're having some difficulty finding the speakers in the preparation room. So if you're a speaker in this session and you've not made it into this room yet, please check for your the Zoom invitation that you will have received with the link to get into the preparation room where you can prepare and enter into the meeting. So while we're waiting for them, I'm hoping that they're online somewhere and just haven't found their way in yet. I'd like to, and I'm very grateful to David Binns, who I think is going to volunteer to go up next and accelerate his talk from the end of this session to now. So going to hand over to David, who's going to talk us about the preparation phase and the outcomes and the future approach of ESA's ISRU demonstration mission. So just while we pull up the slides, to say thanks, David, for being online early and being ready to jump in. And while David's speaking, we'll try and find get our other speakers online.
No problem. I hope you can hear me okay.
Yeah, I hear you. It's good.
Great. It's a brand new headset, so I was afraid that it was not tested enough in advance. Okay, so good afternoon. I'm David Binns. I'm the lead of the ISRU demonstration mission for ESA, and this talks a little bit about the preparation phase outcome, which is recently completed, and the next steps. Are the slides? Oh, yes, there we go. As a sudden start of the presentation, I have got my remote clicker set up, so I rely on James to advance the slides a little bit, if you don't mind. So if you could go to the next slide, please, James. Okay, so ISRU demonstration for a lot of the times so far in its outcome has been a lot about choices. So some time ago, I had a choice to make as like a major purchase for me, and there were a multitude of options. So power, budget, gadgets, need to understand specifically what was needed within a reasonable context. And this is one of the reasons, not knowing those things is one of the reasons why I struggled a little bit with that decision. And somehow the option tree for space resources is also highly complex and completely interconnected. So our preparation phase was really about choosing a feasible and relevant oxygen extraction demonstrator. And naturally, that has been a tricky task for us and our industry. So if you go next slide, please. Yeah. So as a starting point, we looked at a minimum of 100 grams of oxygen extracted from the lunar surface. So, or 90 grams of oxygen shall be produced. This is to sort of create a perception of demonstration and also to set a size of payload which would lend itself to a technology demonstration. So we would learn something from the process of developing this design. I mean, these are payloads themselves. We looked at a target of around 150 kilograms to include an oxygen extraction demonstrator, so an end-to-end demonstrator, as it was called back then, and also early technology payloads and science and prospecting. So we tried to look at the entire package. So for the oxygen extraction payload, which is the focus of this presentation, we looked at more a target of 120 kilograms. And repeatable operations, high temperatures, dust-resistant seal mechanisms should also be demonstrated within this, this package of hardware. To drive the feasibility work for a future plant and to generate the knowledge for a working system in the future. These are the basic things to help us understand necessary lessons and also to be strategically relevant as a demonstrator. So the next one, James. Okay, so the preparation phase began around 2018, 2020. Phase 0 looked at an early mission configuration with ESA forming the teams. Phase A allowed industry to form teams for either payload or commercial service lander providers. Each payload would be interfaced with each service. This, of course, was a lot of interfaces. So we had a selection of concepts early on and of processes. This is largely driven by industry. The MPR assessed all designs. So this is the mission preliminary requirements review. And the recommendation at this point was to look at further processes. So we focused on the carbothermal and hydrogen reduction processes initially. We also want to extend this to the FFC payload up to a Delta preliminary requirements review, which we closed last year. So the next slide, actually. So to mention some results, I mean, there's not the time to look into the detail of everything, but I hope to provide more of a snapshot to give the context of the findings made. So for the moment, will not present the science and technology payloads because there simply isn't time in this talk. But we focused a little bit on the hydrogen reduction payload of ilmenite, which was developed for us by Space Application Services in Belgium. And this led to a mass of around 2 packages of around 70 kilograms, so 2 times 70 kilograms, with total energy consumption of greater than 20 kilowatt hours. And the point to note is this package used tens of kilograms to produce this 100 grams of water, to give a sense of scale and results. They did include a mobility option to potentially mitigate some risks related to accessing ilmenite and a rich enough grade in the vicinity of the lander. And this payload included appropriate recycling of reactants as part of the demonstration. So a further concept we looked at was the carbothermal reduction process, and this was led by OHB Italia. The average mass of this payload was around 100 kilograms and a total energy of greater than 70 kilowatt hours. So there's a little bit more going on in this payload, and this again produced about 100 grams of water in this case. So in a delta phase A process, we looked into the metalysis process. So we asked both those contractors to look at concepts in parallel. This, on average, this payload was about 110 kilograms, and this excavates about 500 grams of oxygen, producing the 100 grams of oxygen. So if I got that right, 500 grams of regolith to 100 grams of oxygen. And we had the gas generating system, the recycling of the system, and oxygen separation and storage. So we had quite complex payloads there. So if we go to the next slide, I hope. So we also looked at obviously the flight opportunities, and we focused very much on the commercial landers. And as we could see that generally our payload masses were not generally compatible with the small landers, which was the 90 kilograms capability of the Peregrine. And we see if you go back one, James, I think you jumped. Okay, thanks. So we're exceeding about 120 kilogram mark with the landers. These things are a bit more possible with the Alina lander that we looked at, and this potentially could meet our needs. In both cases, power was a difficult quantity. I mean, the power generation was not quite, it was close in some cases to our needs, but some far away in other cases. One specific risk that we identified with these interface assessments was the thermal interfaces. I mean, we needed the lander support for our thermal control systems. This is obviously an area of thought in the future. So if you go to the next slide. So despite our low TRL, industry have generated sufficient knowledge of ISRU now, and on the ESA side, internal knowledge has been acquired and the trade of options are somewhat understood. The shopping list seems clearer than at the start. What we think now going forward is we want to optimize yield, production rate, and analyze the generated gases as priorities, along with some key technologies related to loading and unloading of samples. And because we think this is a particular area of risk. The flight opportunities provided interfaces and constraints. So the mass and complexity of the functionality of the payload is limited by the lander. So we wanted to just focus on the extraction of regolith, the extraction of oxygen. But that does not necessarily mean to say that other aspects do not matter and should not be demonstrated. It's just that they may not all fit together at the same time, and options need to be kept open if larger landers become available. So just the next slide, please. So what we're going to do in phase B1, just to conclude the presentation, is with the concept of a nominal and extended mission. And this is the philosophy which has defined the requirements for phase B1. Highlighting processes also made it difficult to move away from the initial choices. So from our feasibility studies and the lessons we've learned from that, we also decided not specifically to specify process, but a set of requirements that would lead towards a future pilot plan, and also set the constraints for the payload interfaces with commercial missions in mind, also keeping the possibility of being a payload on larger missions. This is because we made to be able to utilize the larger mass available. Does not mean to say the demonstrator should be completely all singing and dancing. We still have to define requirements to demonstrate what we believe is the bare necessities for oxygen extraction. So we have to take seriously the investment we make for a space-based development. We need to maintain our openness to potential processes, and since we've shifted to a requirements-driven approach, we have proposed we proposed a challenge phase for phase B1 to select the contractor for that next phase. This will be run in the coming months up to May, and we will select up to 4 contractors, with the winner becoming the prime contractor for phase B1. Challenge, a notional concept evaluation board will be done towards the end of the summer, beginning of the autumn, to get B1 kicked off before the end of the year. So the final slide, James. To just summarize that we've done 4 specific payloads and interfaced them with commercial landers. We have developed payload extraction of oxygen payload concept demonstrated designs for 100 gram of oxygen for varying mass and power requirements. But going forward, we baseline the baseline is just focusing on the sample handling and the oxygen extraction. Pending lander resources, we would look into an expanded reactant gas recycling, storage, or even demonstrating the use of a project should we be able to have the budget, the lander, and so on be available. So we analysed 4 initial concepts in the challenge, and we'll take a single one to the phase B1 for a system requirements review in preparation for our next ministerial. So the focus is basically on a scalable and sustainable concept that leads us to a pilot plant in the future. So thanks for your attention, and I hope it wasn't too much to throw at everyone so quickly. So thanks.
Awesome. Thank you very much, David. And thank you for jumping in to fill a technical problem. Much appreciated. So you posed a challenge in your talk, and a challenge has been posed to you. SpaceX is going to need 100 tons of oxygen in 3 years. That's 6 orders of magnitude increase in mass in half the time. How could you plan to scale that quickly?
It's difficult to say. I mean, we have to move forwards now from our demonstrator concepts to our pilot plant concepts, and launching and landing a plant is a possibility, and scaling it up is a priority for us, and linking that and validating that to our requirements. I mean, the time scale is short and challenging, but I hope we can rise to meet it.
And maybe one more question. Are there any specific risk factors or unknowns associated with the environment and the way that it affects processes or the handling of regolith or the materials that you produce that you need to be answered in order to be able to scale up?
I think some of the key questions we have is the lifetime and reliability of quite complex mechanisms, as we have learned, for the loading and unloading. So it's, in some ways, the engineering challenge is focused more on those sealing, excavating, and having this wear and tear resistance to a very hot, dusty, statically charged environment. Specifically to the processes themselves, I mean, there are a number of unknowns in how these gases evolve in the low G environment. And this is areas where the moon's obviously is a good test bed, and actually using the actual material is quite important. And one risk that's not always mentioned is the operational scenario of these things. So we would like our demonstrator to be a model of what you would do with a plant in the future, so we can learn to understand how we would operate these systems.
Right. And there's one final question, which was, do any of the oxygen production payloads require a specific grain size?
Depends on the process. I mean, we want to avoid fine particles for contamination and plugging of filters, obviously. I won't quote a specific number because it requires analysis to determine. Obviously, greater grain sizes have the potential to plug your chutes and your system so on. But the fines are quite obviously dangerous to mechanisms, and the large particles are generally a clogging risk. Generally, it's quite challenging to process these materials in that environment.
That's great. Thank you very much, David.